So you're studying chemistry, and maybe everything's going great, and you've been learning about things like isotopes and moles and chemical formulas and balancing equations, and then one day your teacher starts using this word stoichiometry a lot, and suddenly there are these calculations that appear and they look really long and scary, and you're like, what is going on? Well, I'm here to help. Stoichiometry calculations, when you first see them, they can be kind of scary. I get it. My job here today, though, is to try to convince you that they're not actually that scary. In fact, stoichiometry is something you probably already do, you just don't call it that. So what is stoichiometry? Stoichiometry is the art of making predictions about quantities of things in a chemical reaction. Like, for example, if I start out with 10 grams of sodium chloride, how much silver chloride should I end up with? Or if I start with 3 gallons of octane in the tank of my car, how much oxygen does it need to fully react? These are kinds of questions where you're trying to make predictions about how much stuff will be produced, or is needed to complete the reaction. I'm going to be starting a series of videos here on how to do stoichiometry calculations. I'm going to start with some simpler ones and move towards some harder ones and show some variations along the way that you'll need, and we'll add to it as the rest of the year progresses. For this starting video though, what I want to do is sort of take some of the fear out of stoichiometry right off the bat and talk to you about how to think like a stoichiometrist, which of course is what you would call somebody who does stoichiometry, and if all goes according to plan, in a couple minutes, that'll be you. Here's a fun example to start with. Let's say I need to make some sandwiches for me and 79 of my favorite friends. And I chose BLTs because why not? Bacon. And I put a simple recipe here. The recipe for a basic BLT is 2 slices of bread, 4 slices of bacon, 1 lettuce leaf, 1 tomato, and if you put that all together, you make 1 BLT. Hold on, forgot to add the mayo. Anyway, if I'm going to make 80 BLTs, it might be helpful for me to make sure I have all the ingredients that I need. For example, how many bacon slices are needed to make those 80 BLT sandwiches? Now you might be thinking of the answer already in your head, and that's great. And what you're doing is actually doing some stoichiometry. You're making a prediction as to how much of something you need to make a certain desired amount of product. I'm going to make it a little more official looking than just sort of staring at a recipe and coming up with an answer in my head. And the way I'm going to do it is I'm going to start with my target. This is what I know that I want to end up with, so 80 BLTs. And in chemistry class, we've been using conversion factors a lot, and I'm going to use a conversion factor here. It's a different type of conversion factor than you may have used before, but it makes use of this, which is your recipe. Maybe you'd agree with me that for every 1 BLT sandwich I make, I need 4 slices of bacon. Now, I want my units to cancel, so I'm just going to make it official looking with this fun conversion factor right there. And I'm going to say that for every 1 BLT, and I'm going to put that on the bottom so that I get my units of BLT to cancel, I need 4 slices of bacon. Okay? And if I do that properly and I get my units to cancel, 80 times 4 divided by 1 is 320 slices of bacon. And I'm going to need to make sure that I have that much bacon if I'm going to make 80 BLT sandwiches. And that is some serious bacon. So just think about the process that you just did to solve that problem. You started with your target amount, and then you took 2 numbers out of the recipe which comprised a ratio. So many of one thing to so many of the other thing, and we put that together into a ratio. We're going to call that a stoichiometric factor just because we like to have big words for things. And it allows us to make a prediction as to how much stuff we want at the end. Let's do another example. Suppose I need to bake a bunch of cookies for the science department bake sale so we can buy more things to light on fire. I've decided to use your basic chocolate chip cookie recipe, which you can find on the back of almost any bag of chocolate chips. Although some chemical formulas have been substituted in for clarity. So first you need 2 cups of flour, a teaspoon of baking soda, sodium hydrogen carbonate, a teaspoon of salt, sodium chloride, 3/4 cup of sugar, 3/4 cup of brown sugar, 2 eggs, a cup of butter, 2 cups of chocolate chips, 1 teaspoon of vanilla, which, if you don't know, is 4-hydroxy-3-methoxybenzaldehyde. Share that at your next party. And if you mix that all together and bake them, you get 24 cookies. So my question is, if I have 14 eggs in my refrigerator, how many cookies could I make? Assuming I had enough of everything else. We could do this the same way. We're going to start with our 14 eggs, which is our starting amount. And I want to go from eggs to cookies. Okay, and I need the ratio for that. Now, according to the recipe, every 2 eggs I put in gives me 24 cookies. So that is going to be the ratio I'm going to use. So 2 eggs, 24 cookies. And a few quick taps of the calculator. 14 times 24 divided by 2. The eggs cancels, and I calculate that I could make 168 cookies with that number of eggs, assuming I had enough of everything else. That's stoichiometry, and most people have done it a million times, they just haven't called it stoichiometry. In chemistry, we do the same thing, only this time our recipe is our balanced chemical equation. Let's say instead of cookies, I want to whip up a batch of diphosphorus pentaoxide. And I know I have some phosphorus and some oxygen laying around, and I know that they react in a 1:5 ratio. 1 of those plus 5 of those is going to make me yield 2 of those. That's my recipe. Now take a look at the question. How many moles of P2O5 could I make using 29.2 moles of O2? I'm going to follow the same exact thought process as I did in my first 2 examples, and I'm going to say, all right, here's my beginning amount. That's how much I know I'm starting with. And then I'm going to create a stoichiometric factor, which you could also call a mole ratio, because those coefficients in the balanced chemical equation tells you how many moles you actually have. 1 mole of this plus 5 moles of that will yield 2 moles of that. Moles don't have to be conserved, but that's what it's telling you. So I'm going to go ahead and take the moles of O2 and put that on the bottom, because I want that unit to be destroyed. And the moles of P2O5 is going to go on the top. The numbers that go there are your coefficients in the equation. So 2 moles of P2O5, let's draw a fun arrow just for fun, and 5 moles of O2, that's where we get the mole ratio, or the stoichiometric factor. And after a quick tap of the calculator, I find out that 29.2 moles of O2 multiplied by 2 divided by 5 gives me 11.7 moles of P2O5. Make sure to highlight your answer. And there you go. We have just made a prediction. With 29 moles of this, I can expect to get 11.7 moles of this. A couple of things to point out here. First, my calculator gave me more digits than I actually wrote down. And that's because significant digits still do apply. I started with 3 significant digits, my mole ratio is an exact value, and I ended up with 3 digits at the end, so I did round that. The second thing that I'd like to point out is that the thought process I used when it looked all chemistry-ish was the same thought process I used when it was making cookies or making sandwiches, okay? Same kind of thing, and we're just applying it to our new recipe, which is our balanced chemical equation. Hopefully some of the scariness of stoichiometry has been taken away, and that you're starting to think like a stoichiometrist. Have a great day.